All right, we finally now get to revisit the fundamental theorem of linear maps and complete the picture. So this has been a long time coming. There's been a whole bunch of dots out there waiting to be connected, and that's what we're going to do here and in the next couple of clips. So way back once long ago when we were in section 3b, and we had theorem 3.22, the fundamental theorem of linear maps. The book presents it just in terms of the dimension of V and the dimension of the null being equal to the dimension of the null space of T plus the dimension of the range of T. But I told you that this was because there's a little bit more going on. There was actually the null space and then some other thing. So back then we didn't know about adjoints, and so this was just some other thing, W, that happened to have the same dimension of the range of T. Okay, and I probably talked about it in terms of null space and row space of a matrix. This actually turns out to be a lot easier to talk about if you've got matrices. So in that case, you've got the row space of A, the matrix of T, and then you have the null space of A, which is just the same as the null space of T. You're just thinking of A as a mapping, and the mapping is T, so it's the same thing. But then, let's see, so then what happened is later on in the picture, we started talking about products and quotients. And so in section 3e, we had the theorem, what was that one? 391. And theorem 391 said that if you do V mod the null space of T, then the resulting thing is isomorphic to the range of T. And so then that tells us that the other thing on this direct sum right here is something that looks like the range of T. By looks like, I mean is isomorphic to. And then, but wait, there's more. We also went on and we saw then in 3F there was a result, theorem 3114, which said that the matrix of the dual of T is equal to the transpose of the matrix of T. And so if we look at multiplication by A going one way, so assuming some basis has been fixed, then coming back the other way is given by multiplying by A transpose. Now, for an inner product space, we're going to change that just a little bit and replace transpose with a star. And we'll see that things become a little bit nicer. But the upshot of all of this stuff that I'm talking about is now we can discuss this picture right here while properly labeling all of the pieces. So the breakdown of V on the one side, this orthogonal decomposition of V, is, well, we've got the null space of V with the direct sum of this part right here. This is the range of T star, the adjoint. Meanwhile, so that's for the mapping that goes this way, that's T. If we're coming back, then the adjoint maps everything into here, that's its range. Similarly, as we're mapping in this direction, the null space is going to be given by this one. And the other part over here, this is going to be the range of the original mapping T mapping this direction. If you want to talk about this in terms of matrices, the range of T, this is the column space, so the span of like the linear combinations of columns of A. This is going to be the same thing as the span of the rows of A transpose. Meanwhile, back over here, we have the range of T star. That's the rows of A, the row space of A, which is the same thing as the column space of A transpose. So it all fits together. And the key important thing is that this vector space here and this vector space here, these guys are isomorphic. So in other words, if you take the restriction of T, so you take T and you restrict it to the range of the adjoint, then this is going to be an isomorphism, and it's going to put this vertical red plane here in bijective correspondence with the range of T over here. All right, and so the point of this next theorem then is to write all that down precisely and concisely. So suppose we've got a linear map from V to W, so we're going this way, right? Okay, then the null space of the adjoint is orthogonal to the range of T. So that's this picture here. Here's the null space of the adjoint, and it's orthogonal to the range of T right here. The next part says that the range of T star is orthogonal to the null space of T. So the range of T stars, that's this part right here, this is orthogonal to the null space of T. That's this one right here. Then the third part says that the null space of T is orthogonal to the range of T star. And at this point you go, oh, yeah, you're just telling me the same thing I already said, that the null space here is orthogonal to this one. Now you're getting repetitive, right? Yeah, and this one here, this is actually redundant with this one. And when we get to the proof, we'll see that we get from this one to this one just by taking the perp of both sides of the equality. Okay, let's go ahead and prove all this nonsense. So, proof for A. Let's take W to be an element of W. and I'm doing that because we're looking at the null space of T star, and T star goes this way. So we're looking at the null space of T star, so we want the things over here in W that get killed by T star. All right, so we're going to take a thing in W and say, what does it mean for it to be in the null space? So then W is in the null space of T star if and only if T star W equals 0. And that holds if and only if V T star W equals 0 for every V. And so here I'm using 612 plus. Okay. And then by definition of the adjoint, I can move it to the other side. TVW is equal to 0. For every V. Now, take a look at what that says. That says that, well, the way to read this is to look at the thing on the left side and interpret this as something in the range of T, right? It's T applied to a thingy, so it's something in the range of T. And so this equality, this last equality that we've obtained right here, is saying that W is orthogonal to anything of the form TV, which is the same thing as saying that W is orthogonal to the range of T. All right. So now if we look at D, if we just take orthogonal complements of A, that gives D by the properties of orthogonal complement. Like if you start with a subspace and then you do the orthogonal complement twice, you end up back where you started. Oh, you know what? I just realized. Yeah, we're only proving this in the finite dimensional case because that result only holds in the finite dimensional case. So that's actually not mentioned in the textbook. But this proof, I guess, only works for finite dimensions. So let's see. But then, and now if we do exactly the same argument going through like this, but we just replace the roles of T and T star, then we get the other ones. So if you just switch T and T star throughout, then that gives you A, and then by taking perps you get C. All right.